So Henry's going to chair this second session on computer experiments.
Well, welcome to the first half of the last afternoon. And again, it's on computer experiments. A very, very important topic. The big bang and very successful. I'm told that the big new Boeing would not be flying without computer experiments. So don't underestimate. Okay, so the first speaker is Peter Qian, who I think I've met before in a very nice conference in Memphis, on nested space filling designs. There you are. Okay. 25 minutes, please.
Okay. It's very nice to be here. It's my first time in Cambridge. Actually, it's my first time in Europe. It's so different from Asia and North America. First, I would like to thank the conference organizer for giving me the opportunity to be here, and also would like to thank every one of you to be here Friday afternoon. This is my title, Nested Space Filling Design. I only have two items. The first one is called Nested Space Filling Design. And this one is motivated by one kind of computer experiment called multiple computer experiments with different levels of accuracy. I'm going to mention two aspects, modeling and design. For modeling, I just mentioned in passing. And I also have another design to offer you, although this one is not in the title. The second one is a bonus part. The second one is also something to do with computer experiment. It's the reason I put these two together. The second one is motivated by another kind of computer experiment. It's a computer experiment with two kinds of factors, continuous and categorical. And for this one, as before, I also mentioned two aspects, modeling very briefly, then design. So this is the outline. Because I only have 22 minutes probably from now, I can guarantee you I'm going to finish the first one, the second one, who knows. So 50% delivery guarantee. Okay, so one advantage of being in the second session is if I want to talk about computer experiments, you already know about definition, so I don't need to introduce much. So I go easy for this part. I just will remind you the interest here is computer experiments, which are pretty different from the traditional physical experiment. Simply put, computer experiments or computer models are mathematical models are implemented in computer code. Because you can have very large computer code, so computational time for computer experiment can also be pretty expensive. And there are many examples of computer experiments. One is finite element analysis, another one is computational fluid dynamics. And people often assume that computer experiments are deterministic. Basically means if you want to repeat the experiment twice using exactly the same input value, you got exactly the same result. So many other properties of computer experiments. Okay. For computer experiment, usually there are two issues. One is modeling. If you get some data from a computer experiment, how can you fit a surrogate model? Another issue is what kind of design are good for a computer experiment. In the literature of computer experiments, people often use a term called space filling design. It's a very roughly defined term. Basically means you want to have a design where the points fill in the space uniformly. So you can define uniformity or space filling in different ways. As a result, you have all kinds of space filling designs. The most popular one so far is Latin hypercube. The reason this one is popular because this one is easy to use and oftentimes give you pretty good result. So Latin hypercubes are proposed by McKay and others. McKay worked for Los Alamos before, and Los Alamos was still the powerhouse, one of the powerhouses for computer experiments. So Latin hypercube have one very nice property. It's called one-dimensional stratification. And this one is going to be very clear in my next example. Constructing a Latin hypercube is very easy. What you do is very simple. For each dimension, you draw a random permutation. Then for each number in the random permutation, represents a small interval. Then you uniformly sample points for each small interval. This is called Latin hypercube. So if you want to know the step here is the steps. Can I go on? So far only introduction, so it's not that important. And you guys know this already, so it doesn't matter. So, okay, so this is the Latin hypercube generation. I want to remind you, actually, Latin hypercube now can be generated in R in a very small package called LHS. It's a very handy one, often used. So let me give you one example of Latin hypercube. So this is a Latin hypercube of 8 points, 3 factors. So basically, if you look at each one of them, each column, you have very good uniformity. So here are the two-dimensional projection for this design. So you have 8 points here. So if you project these 8 points in either this direction or this direction, so in each of the 8 intervals have exactly 1 point. So it doesn't help you have one-dimensional stratification. Okay, so far it's just introduction. Now let me introduce some new stuff. So this is the first experiment I'm going to consider. This is called high accuracy and low accuracy experiment. This one actually become quite popular now. The reason is many computer experiments actually can be run at different levels of accuracy. For example, if you want to run a finite element analysis, you often can control the match size. If you have very small match size, have very accurate result. If you have very large match size, you have very quick result, but not as accurate as the small one. So, and here in my presentation, I consider 2 such experiments I call low accuracy and high accuracy, LE and HE. By definition, basically, HE is more accurate but more expensive than LE. So there are several examples of HE and LE. The first one is you can use 2 different finite element analyses. One with very small mesh, become HE. Another one with very big mesh, called LE. Another example is you can use 2 different numerical methods. The first one uses FEA, which is very accurate. The second one uses finite difference method, which is pretty rough. Okay, there are 2 examples. For LE and HE, usually there are 2 issues. One is data collection, another one is data modeling. Here is the one-page summary for the data modeling. The message is data modeling for HE and LE has been actively studied in recent years. Here are some nice references. The leading work is done by Kennedy and O'Hagan in 2000-2001. The many other very nice work by Los Alamos Group and others. We also done some work. So the message here is very simple. If you have data from HE and LE, what you do? You combine the data to do the modeling. So you want to combine the data. Because HE and LE are different, in the combining data, you want to know what's the difference between the 2. So you somehow quantify difference between HE and LE. In terms of model formulation, most time people use the Gaussian process. But different papers have different formulations, so they're different in terms of model formulation, estimation, prediction. So this is my one-page summary. Okay, now let's talk about data collection. The data collection for LE and HE is a very interesting problem. This is also kind of a new problem in DOE. The reason is classical DOE only consider one source of data. And here what we have 2 sources. They have different levels of accuracy. Before I introduce more, let me give you some definition and notation. And here I'll consider X as input variable or design variables, and assume each one of them is in a small interval between 0 and 1. And I use DL to represent a design set for LE, and DH to represent a design set for HE. So we have DL and DH. Okay, so what we need here is we want to get a design for DL, another design for DH, is what we need. So in order to get a good design, we need to have some kind of principle first. In a joint work with Boshing-Tang and Simon Fraser and Jeff Wu and Georgia Tech, we propose some very simple principles for constructing DL and DH. The first one we call economy. Basically means the sample size of a DH must be smaller than the sample size of a DL. This makes sense because HE are more expensive to get. The second one we call nesting. The second one basically means we require DH is a subset of DL. This makes sense from a modeling perspective. Basically, it means for any point in DH, you have response from HE and LE, so both of them. Because you have results from HE and LE, you can do the model justification very easily. So this one is for the modeling perspective. The second one is more for the nature of computer experiments. Because the surface for LE and HE can be very complicated. So in the design stage, we want to allocate the points as uniformly as possible. So we propose called space filling property. So these are 3 principles. So based on these 3 principles, one question is how can we actually get a design somehow satisfy these 3 principles? So this is not a very easy problem. So actually we have 2 classes of design which satisfy these 3 principles. And today I'm going to talk about the easy one. So in a recent paper, I proposed a new design called nested Latin hypercube design. The reason I'm interested in such kind of design is because Latin hypercube is so popular. So I want to build it on the very good work of existing Latin hypercubes. Okay, the definition is very simple. A nested Latin hypercube, NLHD, is a special Latin hypercube. So what's the special about it? The special about it is this Latin hypercube also contains a smaller Latin hypercube as a subset. So it's a definition. You have bigger Latin hypercube, for example, 10 points. Then for the 10 points, you choose 5 points, become another Latin hypercube. This is called nested Latin hypercube. How to construct a nested Latin hypercube? Actually, there are 3 methods. Let me give you the first method, which actually doesn't work. The first method is the following. You randomly generate a large Latin hypercube, for example, 100 rounds. Then based on this 100 rounds Latin hypercube, you use some kind of random search to search a subset, which is another Latin hypercube with 50 rounds. This method doesn't work. The reason is you have no guarantee a large Latin hypercube contains a smaller one as a subset. There's no guarantee about it. So such kind of top-down approach doesn't work. The second approach works. The second approach works in the following way. If you want to get a nested Latin hypercube, essentially what you need actually 2 Latin hypercubes embedded. So the second way we do it is together we generate a smaller one and a bigger one simultaneously. To do this, we need to use some kind of special permutations, the second approach. The third one, actually, in my mind, is the best one. The third one works very easily. The third one is the following. Suppose I want to get a nested Latin hypercube. What you can do is you can randomly generate a small Latin hypercube. Whatever you generate is fine. You get the existing Latin hypercube, and based on this one, adding more points. You can always enlarge an existing Latin hypercube into a bigger one. For example, you have 5-point Latin hypercube, you put another 5 points, somehow carefully you get a 10-point Latin hypercube. You can always do that, I can show that. So the nested Latin hypercube can be constructed for all kinds of parameter values. They're very flexible in terms of sample size and number of factors. Okay, so if one-dimensional stratification is not enough, you can also do the nested design with more than one-dimensional stratification by using some kind of Galois field and others. So in this paper, we discussed the nested design with 2 or 3-dimensional uniformity. So let's go back to the nested Latin hypercube. So let me give you a few examples. So this is the NLHD of 10 points of 5 factors. So if you look at the whole set, is a Latin hypercube with 10 levels. Look at each individual column, they are very uniform in the interval between 0 and 1. If you look at the points, the 1 to 5, this one forms another Latin hypercube with only 5 levels because we only have 5 points. So this is one. Actually, you can define the nested Latin hypercube in a more general sense. So for this example, we have 2 sets, bigger one and a small one. So what you can do actually here is we have 3 sets. The bigger one, everything together is Latin hypercube with 24 levels. So if we cut this design into half, take the first half. The first half is also Latin hypercube with 12 levels. Now if we want a smaller one, what you can do is you can take a quarter, basically the points from 1 to 6. This one is also Latin hypercube with 6 levels. So you can do the Latin hypercube sequentially. 6, 12, 24, 48, always into infinity, you can do anything. Okay, so for this example, I argue we have 3 layers. The first layer basically means the whole set is a Latin hypercube, 24 levels. The second layer is the half. The first half, the points 1 to 6, and 12 is also Latin hypercube with 12 levels. So the third one is the 1/4, the first 6 points, which is Latin hypercube with 6 points. So let me show some 2-dimensional stratification for this guy. So if you consider all the points together, you got Latin hypercube 24 points, have 1-dimensional stratification. If you only take the first half, Latin hypercube only with 12 points. You take 1/4 Latin hypercube with 6 points. You can always do that. Okay, so far I mentioned about construction. The next issue is more theoretical. I have some formula, but I'm thinking today is Friday afternoon. Would rather not put the formula here. So the nested Latin hypercube actually have very nice sampling property. By sampling property basically means if you want to use Latin hypercube to estimate a sample mean, so what's the property about it? And I can show both in fixed sample and large sample, the nested Latin hypercube are better than simple Monte Carlo. So for the fixed sample, with assumed monotonicity, basically means the function y is a monotone function for each argument. So if we use the next linear hypercube, the sample variance is smaller than the one from the simple Monte Carlo. This one is for a fixed sample. For large sample, you can also show if we use the next linear hypercube, we can achieve the variance reduction comparing with the simple Monte Carlo. So the next property of the next linear hypercube are very similar to a standard linear hypercube. So this means for next linear hypercube, we achieve both. One is a sampling property, another is a very nice structure. Okay, so far I finished the first half of my presentation, so I only have 10 minutes left. Okay, so now let me deliver the second part. For the second part, I want to give you an interesting example first to keep everybody awake. This one actually is based on ongoing work with IBM T.J. Watson Research Center. So this problem is about modeling data center. Data center, roughly speaking, are large machines. So this one is pretty good machine, but this one is a small machine. Large center, a data center basically means you put all kinds of computers together in a very large room. And this one has a huge system for storing all kinds of information. Many IT companies use a very large data center like Google and others. So IBM is a leading provider of large data centers. Okay. In designing a data center, there are many factors to consider. For example, what kind of rack you put here, what kind of thermal property, and what kind of cooling method you use. So many factors to decide. So how can we know a data center satisfies all kinds of mechanical requirements and also thermal property? It's a very difficult problem. So there are two ways for designing and doing research for data center thermal property. The first way is a physical experiment, which is very expensive to do because data center can cost more than several $1 million each. So at IBM, people use very limited physical experiment, spend most time doing computer simulation for modeling a data center computer experiment. And specifically use one software package called Flusen, actually it's a UK product. This one takes into all kinds of factors. For example, the electricity power, like cooling material, and all kinds of other factors. And for this computer experiment, each run can take hours or days to finish. So this one is an expensive one. Okay, now let's talk about something very interesting. Now if I look at factors in this data center experiment, so what we have here is we have two kinds of factors actually. One is continuous one, another is a categorical one. Continuous one like temperature, rack power, etc. For this one, we also have another group which are categorical, like diffuser location and vent locations. The presence of the categorical variables makes the data center study very difficult. So if you go back to the existing literature of the Qian or emulator for computer experiments, there's one assumption is made. The assumption is everything needs to be continuous. So if you look at existing Gaussian process model, basically we assume everything is continuous. Because we assume continuous, we can define distance, we can define correlation, etc. And for our case, we cannot use this because we have categorical variables. Okay, now the question is how can we do some kind of Qian model or Gaussian process model for both continuous and categorical factors? In a recent paper joined with Huaiqing Wu and Iowa State and Jeff and Georgia Tech, we propose a framework for modeling computer experiment with two kinds of factors. The basic idea is we need to define a correlation structure in the space of both continuous and categorical factors. And independently, Gang Han and Tom Santner and Bill Knowles and Ohio State also have another formulation for this problem. It's a more Bayesian framework. So our approach is different from them in terms of model formulation and inference. Okay, so let me move on to the last part of my presentation. I want to discuss how can we do the design for both continuous and categorical factors, like this case. So before I propose the specific design, I want to give you some kind of principles. And before I propose the principles, I want to discuss the two important observations. This is the first one. In a computer experiment with qualitative and quantitative factors, we often find we have more continuous ones than categorical ones. This makes sense because many continuous ones are involved in the finite element analysis, etc. This is the first one. The second one is, for such kind of experiment, you can think the whole system is a bigger one, and at a different level of combination of the categorical factors, you have small systems. And small systems perform kind of differently. So these are two observations we have. So based on these two observations, we propose two principles. So if we want to find a good space-fitting design for qualitative and quantitative factors, we should satisfy two principles. The first one is very easy to understand. Because we know we have more continuous ones than categorical ones. So continuous one probably give you more information. This implies if you just forget about continuous one, the resulting design should be space-fitting. Put it in a better term, basically means a design should be space-fitting when collapsed over the continuous vectors, the first one. The second one is also important because we know we have a subsystem, different level combination of categorical factors. So we require, if we slice the design into different portions respect to the different level combination of categorical factors, we also require the resulting portion become space-fitting, each one of them. If you look at these two, conceptually, the good space-fitting design for the mixture type of factors are similar to the good response surface design with mixed inputs. Okay, so now let me give you the slice space-fitting design. So this one was proposed recently in a joint paper with Jeff Wu. The idea is very simple. So what we do is we have two steps. And the first one is we use the idea of OA-based Latin hypercube proposed by Bo-Xin Tang in the JASA paper 1993. So what we do is we construct a Latin hypercube, OA-based Latin hypercube. And for this one, we need to very carefully choose a very specific OA. So we choose a very specific orthogonal array, and based on this one, get a Latin hypercube. Then the second step, we do partitioning. We partition this one into different groups, and each group corresponding to a level combination of categorical factors. So after this partition, the other portion are space-fitting. I only have 1 minute left probably, so I forget about this one. So let me show you one example. And in order for our construction, we need to define a new discrete mathematical term called sliced orthogonal array. Basic idea is we need to have an orthogonal array, then partition this one in different parts, and each of them become orthogonal array after some kind of level collapsing. So this is called sliced orthogonal array. So here is one example. Suppose we have an experiment involving 7 factors, and among them 5 are continuous and 2 are categorical. For the continuous one, we use a notation x1 to x5, and they are in the unit hypercube 0 to 1. And we have 2 categorical factors, z1 and z2, both have 2 levels, -1 and +1. Okay, and for this one, what we do is very simple. We use a very special orthogonal array in this table, 64 by 5 orthogonal array. So this is an orthogonal array if you consider all the 64 rounds. And this is a special orthogonal array in the following sense. So if you divide this orthogonal array into 4 parts, the first one consider rounds 1 to 4, 9 to 12, 17 to 20, 25 to 28. This part becomes orthogonal array after level collapsing. So other parts also have the same property. So based on this one, we get a OA-based Latin hypercube based on this orthogonal array. Then we do partitioning. So let me show the final partitioning design. So this is the whole design, 64 points. Because this one is an OA-based Latin hypercube, it has 1 and 2 dimensional stratification, so no problem about this. So let's look at first portion. The first portion are 16 points out of this. You look at each one of the projection figures you have, so we have 2 dimensional stratifications. Basically, I mean, if you divide this space into 16 square bins, each one of them has exactly 1 point. So for this portion, is used for the z1 equals minus, z2 also equals minus. So this one we have space fitting. We also have a space fitting for second portion, space fitting for third portion, space fitting for last portion. Okay, so this is all I have. So in summary, what I did here is I proposed 2 designs. One is called nested space fitting design for the multiple computer experiments with different level of accuracy. And second one is called sliced space fitting design for computer experiments with both factors. So I stop here. Any questions? Go ahead.
Okay, in the first part of your talk, when you're talking about the nested Latin hypercube design, does that have a relationship to the sequences that Hugo and Henry were talking about this morning?
Yes. Probably it's more flexible. Here is not, okay. So for the sequences, actually, there are many, many different sequences. I can show theoretically, probably Latin hypercube are better than the Sobel sequences. I mean, in terms of nesting. But for other powerful sequences, like nets actually are better than Latin hypercubes. I can also do the nesting in the nets, which have better property than nesting in Latin hypercube.
Yes, Rosemary.
I just wondered if you could really combine these into a single idea. Because if you take one of your sliced ones,
Yes.
and then you could take your sub-designs to be the first slice,
Yes.
and then the
yes,
first two
yes,
slices,
yes.
and then the first
Yes,
three,
yes.
and so on.
Oh yeah, yes.
So that you could say really it's a single type of design but used in two different ways.
Actually, they are similar as you mentioned, but mathematically they are very different. The first one is only one-dimensional design. It's very easy to do, Latin hypercube. The second kind of design is based on orthogonal array.
But what it's coming up with is similar, isn't
Yes.
it?
So a byproduct of a second design can also be used for nesting.
That's
You're
what I
right.
mean. Yeah.
Just a quick comment. A Sobel sequence is a net.
It's a special net.
It is a special kind of net. So, and the property of having
Let's do it.
one in every cell is
Yeah.
very similar. So. Any other comment here?
Go ahead.
Could you tell us a bit about how you would include the qualitative factors in your Gaussian process model?
Sure.
In 1 minute, maybe.
I'll do it 30 seconds. Okay. So what you need to do here, basically, you need to have two parts. One is regression part. This one is easy. I forget. The second one is you need to do a correlation structure. For correlation structure, what we do is we take a kind of product. So if we have three factors, two are continuous, another one is categorical. What you do is, for continuous one, you just use the distance function. But for the categorical one, you cannot do this. You put a matrix, need to be a special matrix, need to be positive definite. Then put these two together in a model.
Very clear answer. Any other comments? Okay, well, thanks very much.
Thank you.